Welcome to the world of semiconductors. Can you imagine a world without computers or smartphones? Hard to picture, right? Well, none of these would work without semiconductors. In this video, we'll explore how the electrons move in semiconductors and how they enable modern technology. Semiconductors are materials that have electrical conductivity between that of conductors, like copper, and insulators, like glass. The most commonly used semiconductor materials are silicon and germanium. Unlike conductors, whose electrons are free to move, and insulators, which have almost no free electrons, semiconductors have a unique property. Their conductivity can be controlled by external factors like temperature, light, or impurities. This ability to regulate conductivity is the cornerstone of all electronic devices. The behavior of semiconductors can be understood through energy band theory. All materials have two main energy bands: the valence band, which contains electrons tightly bound to the atom, and the conduction band, which contains free electrons that can move and conduct electricity. Band gap is the energy difference between these bands. In conductors, there is no band gap. The valence and conduction bands overlap, allowing free movement of electrons. In insulators, the band gap is very large, making it impossible for electrons to jump to the conduction band. In semiconductors, the band gap is small, about 1 electron volt for silicon, and 0.7 electron volt for germanium, which allows electrons to jump into the conduction band at room temperature. This small band gap is why semiconductors can switch between being an insulator and a conductor, depending on external conditions. In their pure form, intrinsic semiconductors have limited conductivity because the number of free electrons is low. To increase this conductivity, we introduce impurities through a process called doping, which transforms them into extrinsic semiconductors. There are two types of extrinsic semiconductors based on the type of doping, the kind of impurity added. Number 1, N-type semiconductor. Imagine we take pure silicon and dope it with a pentavalent impurity, something like phosphorus or arsenic. These elements have 5 valence electrons, but silicon only needs 4 to form bonds. So, what happens to the extra electron? It becomes a free electron. That means there are more electrons available to conduct electricity. In N-type semiconductors, electrons are the majority charge carriers, while holes, the absence of electrons, are in the minority. Number 2, P-type semiconductors. Now, what if we dope silicon with a trivalent impurity, like boron or aluminum? These elements have only 3 valence electrons, which means they can't completely bond with all 4 neighbouring silicon atoms. And what does that create? A hole. This hole can attract electrons, allowing charge to move through the material. In P-type semiconductors, holes are the majority charge carriers, while free electrons are in the minority. Now, here's where things get really interesting. When we combine a P-type and an N-type material, we create a PN junction, the building block of electronic devices like diodes, transistors, and even solar cells. This junction allows current to flow in a controlled way, which is why it's so important in modern electronics. Okay, semiconductors are everywhere, powering the technology we use daily. Let's look at some key applications. First, we have diodes. They act like one-way streets for electricity, allowing current to flow in only one direction. They're essential in rectifiers for converting AC to DC, like in phone chargers. Next, LEDs or light-emitting diodes. These tiny lights glow when electrons recombine with holes in a PN junction. That's why they're used in displays, indicators, and even traffic signals. Now, the real game changer, transistors. They work as switches and amplifiers, forming the foundation of integrated circuits, ICs. Without them, computers and smartphones wouldn't exist. Then we have solar cells, which convert sunlight into electricity using the photovoltaic effect, a key to renewable energy. And finally, ICs or integrated circuits, millions of transistors packed into a single chip, making devices smaller, faster, and more powerful. They're in everything from laptops to AI systems. Without semiconductors, modern technology wouldn't exist. So, next time you use your phone, remember, it all starts with semiconductors. Can you think of any other devices where semiconductors are used? That's a wrap on semiconductors. From diodes and transistors to solar cells and ICs, they power the world around us. Hope you found this useful. Like, share, and subscribe for more exciting lessons. Keep learning, stay curious, and I'll see you in the next class.